In previous sections, we looked at finding arc length, but we saw arc length when y was a function of x. In this section, we're looking at arc length of parametric functions. So we have a similar equation to do that, but it has changed a little bit since we now have parametric functions. So let's just dive straight into an example and see how this works. Let's find the length of this curve. If you want a visual to begin with, let's see what it looks like. T is going from 0 to 3, so we are finding the length of this red curve. Using the equation from above, the length is equal to the integral from 0 to 3. Those are the conditions on T. We'll take the square root of dx dt. So we're taking the derivative of x with respect to time. That will give us 2t squared. Then we'll square that, plus the derivative of y with respect to t. That is 2t, and we'll square that one, dt. From here we'll simplify. We have the integral from 0 to 3, square root of 4t to the 4th plus 4t squared dt. It looks like we have a common factor with those two terms, so let's factor out the common factor. We now have 4t squared times t squared plus 1 dt. Simplifying a little bit more, the first factor here, 4t squared, is a perfect square. We can take the square root of that to get 2t square root of t squared plus 1 dt. Next, it looks like we'll need a u substitution in order to evaluate this integral. Let's let u be the radicand, 2t plus 1. The derivative of u is then 2t dt. Now, when we rewrite the integral, the limits of integration change. So initially we had 0, plug in 0 for t, and we get the lower limit 1. Upper was 3 to begin with, plug that in, 3 squared plus 1 will give us 10. And now 2t dt is really du, and under the radical we have t squared plus 1, which is u. That is the square root of u du. So much simpler. We can now integrate this. We get 2/3 u raised to the 3/2, and we are evaluating from 1 to 10. That is 2/3 times 10 raised to the 3/2 minus 1 to the 3/2. That will give us 2/3 times 10 root 10 minus 1. And we now have the arc length. Let's find the area enclosed by the parametric curve and the y-axis. To begin with, we'll look at a sketch in Desmos. I've already got the equations in there. We'll just hit play to watch the sketch. And what we're looking for again is the area between the curve and the y-axis. So back in our notes, let's just do a quick sketch to visualize what we're looking for. Again, just very rough sketch. We're looking for this area. The first thing we need to find is going to be those limits of integration. So we want to find those y values. This point and this point. To find those values, notice what value x is. Since we're on the y-axis, x has to be 0. So over here, let's let x be 0. Then 0 equals t squared minus 2t. And solving the quadratic, we'll factor out t. Set each of those factors equal to 0. And we get that t is 0 and t is 2. To find the corresponding y values, we will plug those in for t in the y equation. So y equals the square root of 0, which is 0, and y equals the square root of 2. So we now have the two y values that we need. 0 and square root of 2. Those will be our limits of integration. To find the area now, we're going to integrate from the rightmost x value, I'm going to call that x sub r, minus the leftmost x value, call that x sub l. And for now, we're integrating with respect to y. So our area is the integral from 0 to the square root of 2 of the rightmost x value, which is 0, minus the leftmost x value, which for now we're just going to call x. And we again are integrating with respect to y. Simplifying this, we can pull out the negative since that's just a constant. We have the integral from 0 to root 2 of x dy. At this point, we want to make sure we have the same variable. We're going to replace the x's and the y's with something in terms of t. So when we rewrite this area, we'll have negative integral, and since we're changing our limits of integration, right now these are in terms of y, we want them in terms of t. We'll come back up here to this equation. The square root of 0 is 0, so our lower limit stays the same. And then if we plug in the upper limit for y, the square root of 2 equals the square root of t. Squaring both sides will give us the upper value has to be 2. Now replacing x with something in terms of t, we have an equation that we can use. X is now t squared minus 2t. And we also want to rewrite dy so that it is also in terms of t. So let's take the derivative of y. The derivative of the square root of t is 1/2 t to the negative 1/2. And that is dt. Simplifying once again, we get negative integral from 0 to 2. Distributing through those parentheses, we'll get 1/2 t to the 3/2 minus t to the 1/2 dt. Now it looks like we've simplified. We can finally start to do the actual integration. We'll get negative 1/5 t to the 5/2 minus 2/3 t to the 3/2, and limits of integration 0 to 2. We'll next plug in those limits. Negative 1/5 times 2 to the 5/2 minus 2/3 times 2 to the 3/2. And technically we're subtracting 0. That's not going to change anything. Simplifying a bit more. I'm going to pull out 2 to the 1/2 power. I think that's going to make it a little bit easier. That will leave us with 4/5 minus 4/3. And then simplifying that, we have negative root 2 times negative 8/15, which is positive 8/15 times the square root of 2. And as a reminder, that value is the area between the curve and the y-axis. In Calculus 1, we noticed that if you take the derivative of a position function, we find the velocity function. Well, we can do the same thing with parametric equations. If the parametric equation represents the position of a particle at time t, then taking its derivative will give us the velocity function at time t. In this example, we have parametric equations. Let's find the velocity at time 5. First, v of t. V of t is the square root of dx dt. That is the derivative of x with respect to t. That will give us 2. And we want to square that. Plus dy dt, the derivative of y with respect to t. That is 4t minus 3, and we square that piece. From here, let's simplify just a tiny bit. We'll get the square root of 4 plus 4t minus 3 squared. And we want to know v at 5 seconds. We'll just plug in 5. 4 plus 4 times 5 minus 3 squared. That is the square root of 4 plus 17 squared. 4 plus 289. That is the square root of 293. And if we wanted to approximate that, that will give us roughly 17.12 meters per second. This again is the velocity when time is 5 seconds.